Yes, thank you very much to the organizers for inviting me. I'm happy to kick off this introductory conference. So I will give two talks on Equivariant Thom spectra. The first one will be sort of about elementary and fundamental properties, what's known, what was proved a while ago, and then the second I will talk about equivariant MU in particular and equivariant chromatic homotopy. So I'll start with recalling a bit what we know about classical MU. So MU is a complex Bordism spectrum, plays a central role in stable homotopy theory, and it has a lot of desirable properties. First of all, it's a geometric object. When I take the homotopy groups of MU, I can interpret that as Bordism classes of manifolds. And more precise, of so-called stably almost complex manifolds. So complex structure on their stable normal bundle. And then one can define the notion of Bordism on these, and one gets a Bordism ring, and that's the coefficients of MU. The second nice property is that it's sort of topological or maybe homotopy theoretic. So it classifies complex orientation. It's the initial complex oriented theory. In other words, if I look at a set of ring maps from MU to another homotopy ring spectrum E, that set identifies with a set of complex orientations on it. So if I have such a complex orientation on here, I have Thom classes, a theory of Thom isomorphism, theory of Chern classes, and so on, and MU is the initial object in that category. And the third one is algebraic. And it's another universal property of the coefficients, or another description of the coefficients. Namely, when I take the evaluate, so MU is a spectrum, I can take the cohomology, it forms a cohomology theory, I can evaluate that on CP infinity. I have a canonical class, Euler class, and this pair forms a formal group law. This is the case for every complex-oriented theory, and in that case, it's the universal one. So this is Quillen's theorem, and in particular, it says that there's a canonical map from the Lazard ring to the homotopy groups of MU, and this map is an isomorphism. So that's Quillen's theorem. Okay, so these are sort of three important properties of MU, and one can play them off against each other and learn, get a lot of information. There's a similar version, so I want to talk about MU and MO in parallel. There's also unoriented Bordism. MO, and it also satisfies these three properties, but in the real setting, so 1 plus 2 are analogous. One just replaces, so here it becomes simpler, it's just actual manifolds, smooth manifolds up to Bordism. The second one talks about real orientations. And then the third one, this was also proved by Quillen, one evaluates at RP infinity, and what one gets is the universal two-torsion formal group law. I will abbreviate formal group law of FGL. And what does two-torsion mean? It means that the two series of the formal group law that I get when I plug in the same variable twice is 0. Okay. So I'm guessing that Vesna will say a lot more about that part in her talks. I will for now mainly focus on the first two. And now go in the equivariant direction. So if one tries to do the same thing equivariantly, the first disappointment is that there's no spectrum that satisfies 1 and 2 at the same time. So no G spectrum for any, so this is true for any non-trivial group G, no G spectrum satisfies 1 and 2. These don't sort of work together. What's the proof of this? How does one see this? So first, if I want something that satisfies 1, this would hint at a geometry, at a connective theory. Right? There's only manifolds in positive and non-negative dimensions. It doesn't really make sense to speak about negative dimensional manifolds. So this 1 needs a connective theory. But one can show that no connective theory can be the universal complex-oriented spectrum. And why is that the case? So, no connective E or G spectrum is satisfied 2. And I just give an example for the group of 2 elements. Take G equals C2. I denote by sigma the complex sign representation. And then a typical construction one makes in equivariant homotopy theory is one starts with a representation and then one forms the one-point compactification and one gets a sphere. So as sigma is the one-point compactification. Or another way to say this is one takes the Thom space of, I can think of my representation as a bundle over the point. This is a G equivariant, a C2 equivariant bundle over the point. I can take the Thom space and I get a sphere. And the reason I formulated this way is that if I have a complex orientation, I should have Thom isomorphisms for complex vector bundles. Okay. So if
those sigmas look a bit more fused.
Yeah.
I try to avoid it looking like a 0. Okay. So if you now take a complex-oriented theory, so C2 spectrum, then we can make the following construction. So first, if I smash my spectrum with S sigma, so as I said, this is now smashing with the Thom space, so there should be a Thom isomorphism. So this is going to be equivalent to E smash S2, since underlying is 2-dimensional. But I have an interesting map into this. So here I have a map from S0, so this is now a 0, into this just by taking the unit on E and including the fixed point of S sigma into here. So this is often called a pre-Euler class, and we will denote this by A sigma. So this class exists for any C2 spectrum, but when I have a complex orientation, I can identify this with just a twofold suspension of E. So I get a composite like this. And this we will denote by E sigma, and this is the actual Euler class. Okay. So that means that I have a canonical element. So this just represents an element in the homotopy groups of E, the C2 equivariant homotopy groups of E, but it's of the degree -2, goes from S2 to S0 to S2. And so this Euler class is an element in pi -2 C2 of E. So what was sort of happening here is equivariantly one has interesting, in general, non-trivial maps that go between spheres that go up in dimension. Okay. And that's sort of not a problem if this is just a fixed, if so the fixed point dimensions match up. But if I have a complex orientation, I get an honest map from a 0-dimensional thing to a 2-dimensional sphere. And in general, that's not a problem. So if E is connective, that just means that this class is 0. Okay, that can happen. So there are examples of complex-oriented theories where this happens. But remember, we are looking for the universal complex-oriented theory. And to satisfy one, we needed a connective theory. So we need a connective theory to be the universal one. But if it's 0 for the universal one, it would always be 0. So to show that no connective theory can satisfy 2, I just need to give one example of a equivariantly oriented theory where this E sigma is non-trivial. And one can take Borel's homology for this. e.g. if I take F Borel cohomology for F2 cohomology is Borel theory. This is complex orientable or complex oriented. In general, if I have a non-equivariantly complex oriented theory and I take the Borel construction, I always get something equivariantly complex oriented. And one can compute that in this case so if I compute the minus second homotopy group of this identifies with the second cohomology group of BC2 coefficients in F2. This is isomorphic to F2 exactly by this Euler class, so it's non-trivial. So there exists a theory where this Euler class is non-trivial, which means it must be non-trivial for the universal theory, which means that one cannot be connected. Are there questions about that argument? And that works for any non-trivial group. So the upshot from this is that there's really different equivariant generalizations of mu and mo. And I will use the notation from the book of Stefan Schwede, which is generally a very good resource on or reference on what I talk about today. So there's a geometric theory which is written by a lower letter M OG and MUG, so those are the geometric theories. They go back to Connor Floyd. I'll just write a few names, Stone and Wassermann. And then there's a different family of theories which are homotopy theoretic Bordisms. So this will be known by capital MO. So these are homotopical or homotopy theoretic. And they were defined by Thom D. And then there's another one which is important, but which I won't say a lot about, which is sort of specific to the group C2. There's also what's called real Bordism. So this is just for the group C2. This was defined or introduced by Landweber or independently Fuji. Sure. And this is sort of special as the last one studies the relationship between MO and MU, and it uses C2 equivariance. So this is specific in the sense that when I take the underlying spectrum of this, I get MU. And the C2 geometric fixed points of MR and MO. So I will not say a lot about this, but I'm guessing that maybe this will appear in Vesna's talk as well. Okay. I will focus more on the first two. So now in what sense is the first one geometric? In what sense is the second one homotopy theoretic? What are the theorems? So the first theorem goes back to Wassermann, or it's usually attributed to Wassermann, at least because it follows from a transversality theorem that he proved. And this is in the case where G is finite, the product of a finite group and a torus. So in particular for finite groups or for tori this holds. Then one can take general G space or cofibrant G space, and one gets that one takes the equivariant homology theory, which is defined by the spectrum MOG, little MOG, evaluates it at X. This has a geometric description. So this really identifies with the geometrically defined Bordism theory. So this is really, and looks at Bordism classes of a G manifold, compact smooth G manifold into X, and looks at Bordism classes of these. So I didn't say this here, but really the geometric property is not just about the coefficients, but the whole homology theory represented by MU has a geometric description. And this works also here. So, and one can show, so this is not just because the proof doesn't work any more generally here than for these groups. If G is not of this form, then this actually doesn't work. So the homotopy groups for a more complicated compact Lie group of this, or the homology represented, will not have this geometric description in general. But it works for finite times torus. And then about the homotopy theoretic. So that theorem goes back to Cole, Green, Lees, and Kirsch in O2. And there's also a contribution by Julius Krönjes very recently. So if G is abelian, then MUG is the initial complex-oriented G spectrum. And in the unoriented case, this is just known for the real tori, Z mod 2, the elementary abelian 2 groups. So in that case, MOG is the initial real oriented G spectrum.
Markus, can you look at board number?
Ah, this one is not readable. Sorry.
So I have a question.
Yes.
So in the Wassermann's theorem, is it that for other groups there is no representing spectrum, or just this one doesn't work?
There does not exist, so sort of the transfers behave wrong, in the wrong way, they don't fit together. So there does not exist a genuine G spectrum which represents this. I guess there's probably a naive one if you don't ask for transfers. But no genuine theories. More questions? And in that case, I think there's really work to do. So it's not the case that this can't work for other groups, it just hasn't been proved yet. So the methods don't translate directly. Okay. So now we have two different theories, and I want to say a bit about the relation between the two. So first of all, there's comparison maps. In the complex and the unoriented setting. And very recently, Abu Zaid and Bai proved, this is a preprint that just appeared in December last year, that if G is finite, then the induced map on homology theories, so and again X is a G space, and this is always injective. So the homotopy theoretic bordism is always larger than the geometric one. And this was known a lot earlier by work of Löffler on the level of coefficients, and there, but only for abelian groups, but they are also for tori, so it doesn't have to be finite here. He showed that on the level of coefficients, this is injective. So there's one thing to say about the relationship between the geometric and the homotopy theoretic, and one can make the difference quite precise in general. So there exists a class, canonical class in the geometric theory, which I call TV. So V is a representation, and this exists in the geometric bordism picture. So now this is just the geometric picture again. This also maps to the little MO. And how is this class defined? As a canonical class, namely I can take the identity of SV and make sense of this as a class in here. So the geometric bordism class means I have to take a G, a compact smooth G manifold, together with an equivariant map into the space on which I'm evaluating. If I take a representation sphere, I can take the representation sphere on both sides. because this is also a complex smooth G-map, or it can be given the structure of a complex smooth G-map. So one just takes the identity, this defines a canonical class in there, and Brücker and Hook '75, they showed that, and this actually works for all complex D groups and any G space, that if I invert this class, so if I invert these classes, this is running through all the representations, all the reducible representations at least. And what does it mean to invert? So I have an external product on these borders and theories. So I can multiply over and over with this class TV, and I'm really adding larger and larger smash powers of SV to X. And if I form this co-limit, then one gets the same thing as if I evaluate the geometric theory on X, and I invert this class. So there's always a map from here to here. And it's also the same as the homotopy theory. So if I form this co-limit, then all the theories are the same, and in here the class is already invertible. And the reason it's invertible in here is that this class T is sort of the inverse of what a Thom class wants to be. So this geometric theory doesn't have Thom isomorphism, yes, it's not real oriented, but sort of the inverse of what a Thom class for this bundle, for this Thom space would be already exists. And if I invert it, then I actually get Thom classes in general. So this is sort of stable real borders. So in some senses also as a geometric description, but I have to take this co-limit of geometric bordism classes into spheres. Are there questions about this?
So I have a question about notation.
Yes.
When you put MOG subscript star, you're meaning the G maps from the G equivariant bordism of MO into X.
I mean, on this side, this is pi star G MOG smash X. And here, I mean, maps from the bordism classes. These are G maps. Is this okay? Any more questions about this? So I can always make sense of the completely geometric theory. There's a Thom-Kontriagin map that goes from here to here. I can post-compose with here. This first map is only an isomorphism at finite times torus. But if I invert the Thom classes, sort of the transversality issues go away, and I have isomorphisms all. Oh, sorry.
Something similar to that result also work in complex ones?
Right, so the literature is not completely clear in this area, so this is often assumed, but I'm not aware of a reference where this is proved. Yes. So this is also, well, this first one, for example, in Abu Zaid Bai, this is claimed that this also works in the complex setting. And it's probably true because the Wassermann transversality also works there, and that's the main ingredient in one of the proofs. But I'm not aware of a reference where it's actually written down. In a similar situation there, unfortunately. Best way to erase the board. Yes, and I want to say one final thing about the relationship between geometric and homotopy theoretic, and that's the result of Hanke, Bernhard Hanke from 05. And this only holds for tori. So we looked at this relationship on coefficients, and he compares it with the relationship on geometric fixed points. So for G spectra has different notions of fixed points. These are sort of the homotopy groups of the categorical fixed points. These are the homotopy groups of the geometric fixed points. Oh, yes, sorry. And for Thom spectra, in general, the geometric fixed points are easy to compute because they, in a sense, they commute with Thom spectra. So Thom spectra are like generalization of a suspension spectrum, and maybe you know that geometric fixed points of suspension spectra are easy to compute. They're just the suspension spectra of the fixed points. And this carries through to Thom spectra. So generally, these are sort of easy to understand, but these are the interesting ones. One has to try to get information from the geometric fixed point side to the categorical fixed point side. And this is a situation where this is the case. So this can be computed completely explicitly. So it's going to be an algebra over non-equivariant MU. And since this is the non-oriented theory, I will not have the Euler class, but I sort of have the inverse of it already. And then there's further classes using Bernhard's notation equals ydv. So the polynomial ring on these classes, this ranges through all the non-trivial irreducible representations. And this varies through all the positive integers. And here it's almost the same, except that here I do have a complex orientation, so the Euler class already makes sense. So here I have EV plus minus 1, and then the same classes as before. So on geometric fixed points, the difference between the geometric and the homotopy theoretic setting is just that here I have a polynomial ring, and here I have a Laurent polynomial ring in these classes.
Need a G? Oh, no.
Well, I mean, this is implicit in what V, and so V ranges through all non-trivial reducer.
They're just formal variables over there.
But they're just formal variables. And Hanke showed that this is a pullback. So I can check, if I have a class in the homotopy theoretic Bordism ring, I can check whether it comes from a geometric class by just checking whether the Laurent polynomial is an actual polynomial. It doesn't involve any positive powers of E. And Moritz Fiersching proved the analog of this in 2012. He proved the MO analog of this, or the MO analog of tori, which again are the elementary abelian. Okay. Are there any questions about this? So generally, and most of what I say from now on will be about that case, we understand the homotopy groups at abelian groups fairly well in the complex setting and at elementary abelian 2 groups and in the unoriented setting. And beyond that, it's very mysterious and not well understood. So, and this is the first instance of this. If I look at more complicated compact Lie groups, right, I didn't say this. In this case, these maps are actually also injective. But this is only true for tori and here for elementary abelian 2 groups. So this really embeds into a large polynomial ring, and this embeds into this Laurent polynomial. So now I want to talk more about the homotopy groups and what the main tools are to compute and understand them. first tool are sort of characteristic co-fiber sequences. So these are among the, I would say, the main tools generally in G-equivariant stable homotopy theory, but they're particularly important for Thom spectra. And they originate from two co-fiber sequences in G spaces. One is for the group C2, one for the circle. So this is again a sigma, and now I'm cheating slightly. This is now the real sign representation, not the complex one. So there's a co-fiber sequence of C2 spaces of this form. And where does it come from? You can think of a C2 cell structure on this, where you have the two fixed points and then a single free cell. Or you can think of this as sort of the sphere inside the sign representation. And then there's always, this is a one-point compactification, this is the sphere inside, and one is always the unreduced suspension of the other. Okay, so this is a co-fiber sequence which connects of two orbits. This is the orbit of C2, so C2 mod C2, and this pre-Euler class A sigma that we talked about before. And there's a similar one for the circle group. And here, the representation that shows up is the tautological circle representation, the tautological one-dimensional complex one. So this is in T spaces. And this is the tautological T, or one-dimensional T representation. So I have these two co-fiber sequences, and I can get more by pulling back via group homomorphisms to those two. So if I have surjective group homomorphism from any compact Lie group G to C2, or a surjective one to the circle. So these are really sort of just characters in the real sense and here in the complex sense, and I need them to be surjective. Then one can pull this back. And since it's surjective, this will still be a transitive G set, namely G mod the kernel of V. And here I get the pre-Euler class for my character here. And this is now in G spaces. So this way I get lots of co-fiber sequences of this form, and they play a central role. So I have a co-fiber sequence and I can map it into a G spectrum and I get a log exact sequence. And I will now do this for these spectra MU and MOG, and I'll just tell you what the outcome is and explain why that's where one arrives. So the claim is that if I look at the associated log exact sequence for capital MO, I actually get a short exact sequence. And I will now do this in the case where the character is the projection from G times C2 to C2. And it's of this form. So here I'm multiplying. So here I have Euler classes and I multiply with the Euler class. So I land in the same. Like this. And then the co-kernel is the restriction map. Like this. So the claim is this is short exact. I can do a similar thing. So this is short exact for any G. I can do a similar thing with MU. And so E sigma now, sigma is just means I take sigma on the C2 part and trivial on the G part. And here I have a restriction map again. Like this, and the claim is these are exact. And then there's also one for little mo. This is a bit more complicated, because here I don't have the Euler classes, but I just have pre-Euler classes, and I need to incorporate this. And it doesn't work in all degrees. So here I now have an A sigma. And again, a restriction map. Sure. So now maybe I should say a word about this now. So this is now using so-called ROG graded, or at least representation graded homotopy groups. So here, this star denotes still ordinary Z grading, but I allow to subtract an actual G representation. So this is a G representation, and it also only works for G elementary abelian. Again, and now I should finish, so now I have to restrict this to, and I will get a restriction of this representation W to W to G, and I get a short exact sequence again. So the claim is these are all short exact. So, and the reason this shows up is these are the degrees which can be still described geometrically as Bordesson groups of representation spheres. So another way to say this is isomorphic to n star G times C2 of SW. So in these geometrically characterized degrees, one still has a short exact sequence. Now I want to say a few words on why this is the outcome. What does this use? First, I'm using the real or complex orientations of MOG, MUG. So let's try to do this together. So I have this cofiber sequence here. Let's do the MO case. And I pull it back to G times C2. I get another cofiber sequence. Now I'm mapping this into capital MO. Mapping this the zero sphere into capital MO is just the homotopy groups of capital MO. Mapping this into capital MO, this is now a Thom space, and I have Thom isomorphisms for capital MO, so I can make this into the ordinary homotopy groups as well, and this is what shows up here. And then I have the last term. This one is mapping from a free or from an orbit. Then as a property, if I map from an orbit, so this would be G times C2 plus, or G times C2 mod G. If I map from this into a G spectrum, what I get are the G homotopy groups. So the quotient in the orbit. This is why this shows up. So that explains why I would have a long exact sequence, and now why do I actually get a short exact sequence? It's because I have a section here. I actually have a map from here to here. And this is an inflation map along the projection. So usually for G spectrum I can only restrict to a subgroup, but for global spectra I also have an inflation map along surjective maps. So this uses a global structure. Global structures of So this implies that when I look at the functor that assigns to a group G, the equivariant homotopy groups of MOG, so I will just do it for the geometric one, this has inflations, i.e. one can pull back along any group homomorphism, so it's a functor contrarian functor from category of groups to abelian groups. So it's sort of a global family of equivariant spectra, and they are related along these Pullback homomorphisms. And because the inclusion of G into G times C2 has a section on the level of groups, that means that the restriction map will also have a section. Okay, so if I have a section here and I also have a section here for the same reason, that means in particular this map is surjective, so it breaks up into short exact sequence.
Markus, could you have symmetric sorry, there's no. Okay, it's the wrong way.
It's the wrong way. Yeah, I mean, this is not the largest generality where you have something like this. It's true. And then for the third one, I wanted to give these names. So let's call this star 1, this star 2, and this star 3. And for the third one, there's an additional, the argument is a bit more complicated, but the key is that one has these classes TV. So the existence of these classes, which have the property that they restrict to 1 at the trivial group, forces these sequences to fall into short exact sequences. And here one really needs that it's in those degrees, and there's a more complicated argument. Because here, even though I have a section, I cannot always arrange a section in a way that this W bar is really mapped to W. So it's more complicated, it's an inductive argument. And we only know how to do it for elementary B.
Markus? Yes, so in the statement you said that W was a G representation. What should be a G times C2 representation?
Ah, yes, sorry. Thanks, good point. No, it can be a G times C2 representation. Is this readable? So I said earlier that these co-fiber sequences are particularly useful for Bordism, and that's exactly because the long exact sequence that one in general only gets really breaks up into short exact sequence. This is easier to work with in a strong application. So what's one reason why is this useful? So from these short exact sequences we get an operator. It works for all three theories, but I'll just do it in the little MO case, which raises the degree by 1. And how is this defined? So I do it on the board. So here I start with the situation where W is trivial, so I'm in an actual integer degree. And now there I do have a section, and I can restrict and inflate again. And if I then take the difference of the class I started with this new class, this will map to 0 here. If it maps to 0 here, it means that this is divisible by A sigma. And so this is the definition. I take the difference of x and the projection to G of x inflated. So I have the map from G times C2 to itself, where I just project into to G. And this will now restrict to 0 at G. And I want to make it divisible by A sigma, but I first have to multiply with this class T sigma to move it to the right degree. So in some sense, this is sort of dividing by the Euler class. This might not be divisible by the Euler class directly, but I can sort of subtract the 0 coefficient of it, and then I can divide it by the Euler class. And this works for all three theories, but here, in this case, it also has a geometric description. And it's actually, this construction is older than this algebraic description due to Connor and Floyd. They showed that if it's represented by a G manifold M, the Bordism class, then you can write this as, you take the product of M with C2, with S1, and you think of S1 as a C2 times C2 space, where you have the -1, the antipodal action, and complex conjugation. You use the -1 action to equalize here, and then you use the complex conjugation action to get a new involution. So this has a geometric interpretation, and why is this operator useful? So all the computations that we have of these equivariant Bordism rings use this operator. The first one is theorem of Alexander in 72, so he gives a basis of the geometric C2 equivariant Bordism ring. This is also in terms of this operator, and simple pieces which are just the projective spaces in the representation of the form, this one copy of the sign representation and then n-trivial copies. I will not spell it out completely, but it's relatively the simple formula in terms of these classes. The Sinha did the same for basis of the homotopy theoretic Bordism ring for C2. And Dev Sinha also, maybe basis is too much, but let's say a formula. In the circle equivariant homotopical Bordism frame. Okay, so all the descriptions that we have, so maybe I should say in general, these rings are a lot more complicated than the non-equivariant analogs. So the non-equivariant Bordism ring, complex and real, is just a polynomial ring on classes that we understand well. These are not going to be polynomial rings, they're much more complicated. And all the explicits of generator relations description that we have are written in terms of this operator.
Can you say again in Alexander's result what the last symbol was? The P is seen across?
It's a projective space in the C2 representation sign direct sum Rn. Thank you. I want to say one more thing, but time is running out a bit on this, so I'll just say it in words. One other thing one can do with this is, so I said that one can think of this operator as sort of analogous to you take a power series, you get rid of the zeros coefficient, and then you divide by the power series generator, and you get a new power series of 1 degree larger. And this can be mighty precise in that there's actually a map from this ring into a power series ring over the coefficients, the G-equivariant coefficients of MO. And so defined exactly and by just sort of iteratively taking the zeros coefficients of these gamma operators. And you can use this map to detect when a class from the geometric fixed points can be lifted to an actual geometric class. This is a result of Portman. There's another pullback result sort of similar to the one by Hanke, which shows that if for the group C2, the coefficient ring will embed into the geometric fixed point ring, and I can check whether a class is actually geometric by taking a map to a Lorentz power series ring and checking whether it's an actual power series. So an integrality result. So then I will wrap up. I will just state a theorem which I will also use as a starting point for equivariant chromatic homotopy theory next time. So these short exact sequences that we developed, they actually characterize the homotopy groups. That's what the theorem says. Due to me. So on elementary abelian 2 group, when I take the homotopy groups of this global MO, so I just think of it as a functor, contravariant functor on the category of elementary abelian 2 groups. This is initial under functors which also have these Euler classes EV, so just classes which live in certain degrees, such that the analog of this sequence is exact. If I take any functor from elementary B in two groups, contravariant to commutative rings, it also has classes which live in the right degrees, with the property that the kernel of the restriction maps has the Euler class as a regular generator. Then it receives a unique map from the homotopy groups of MO. So it characterizes the homotopy groups of MO. And you can do the similar analogous thing with MU, but there you have the abelian groups. So this is initial with Euler classes. Such that the second one is exact. And also one together with Stefan for the last one. And here I'm not going to make it precise completely, so this is only in the degrees of the form integer minus a representation, just the ones that show up there. So this is again on elementary abelian 2. This is initial, where now I need the classes, both the pre-Euler classes A, V, and these classes T, V, such that this last one is exact. It takes a bit of time to define what this algebraic category is exactly, but the upshot is that these short exact sequences which show up and which were always implicit in these previous descriptions of explicit computations, they're sort of the really characterizing thing of equivariant Bordem rings for these groups. And in principle, one should be able, anything one wants to say about them, one should be able to derive from these short exact sequences. And on Wednesday, I will start with this and sort of describe equivariant, or say something about equivariant chromatic homotopy theory from this point of view. And I'll also explain how this relates to the classical equivalent theorem. Because this is not phrased as an algebra over mu star, but this is so as a full functor on all tori. So in particular, it refines the classical equivalent theorem, but it's also used in the proof. It's not an independent. Okay, and I think I'll stop here.
Questions? More questions? Yeah?
Right, I'm not sure if this is a preview question for next time, but so what are some spectra we might know that that satisfy this property that get these maps from these global?
Right. So for little MO, the main example is Verdun for the constant coefficient. And then you can sort of form smash product of these. And these smash products also have universal properties in this language. And then for MU global, well, the prototypical example would be global K theory, global equivariant K theory. Where then you have Borel theories of complex-oriented spectra. But we don't have as many examples as we want, I would say. The natural question is whether there's a higher height analog of this on a global, non-complete form.
Other questions?
You read that the homotopy category or the geometric one has an analog of the algebraic description, something similar to before?
Yes, so right, I think I'll say more about this next time. But you can think of a sort of a functor with these short exact sequences sort of as a decompletion of a formal group law. So in particular, you can always complete them and you land in a subcategory which is equivalent to formal group laws. So that's one answer. And another is, instead of asking for a universal property for the family like for the functor at all groups, you can look ask for universal property at a fixed group, right? And there's also a theorem, so you can also show that there's an A equivariant Lazard ring defined by John and Cole and Krish, and this is isomorphic to the A equivariant homotopy groups of MUA. It's a different point of view. And yeah, I think in some senses the global one is nicer because you don't work with complete rings. It's sort of a decompletion, and the sort of the main classes that I will talk about next time, they all arise from these short exact sequences. So I think that's a good point of view. But you can also fix a group A, and then of course there will be examples which just live at that fixed group A. You can't lift everything to a global theory.
Any other question? Anybody on Zoom? Doesn't seem to be the case. So now we have a coffee break and we'll meet again at 11:45 and thank Markus again.